Welcome to the Introduction to Calculus. I'm Mr. Stark. This video is about limits and motion, the area problem, which is topic 2 in the video series. The focus is on definite integrals, which help us solve the area problem. We'll be working through this document, which is linked in the description. So let's get started. Since we'll be working with Riemann sums, let's do a quick review. Let's find the sum of these two expressions. They both have the Greek letter sigma, and when we use the capital letter sigma, it means add things up in mathematics. It even shows up in spreadsheets as a button that you can use. So number 1, the Riemann sum from 1 to 5 of 3i. What that's telling us is to plug in 1, 2, 3, 4, and 5 in for i, and add up those 5 expressions. So we get 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 plus 3 times 5. And that is equal to 45, which we could calculate in our heads, on paper, or on the calculator. There's even a shortcut on the TI-84 for Riemann sums. Number 2, pretty much the same setup except we have I squared. So again, we'll plug in 1, 2, 3, 4, and 5 for I. And by the way, we always plug in whole numbers. So that means we get 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Add all those up, we get 55. And that's it. That's how we work with Riemann sums. Calculating distance traveled is a common thing we do in calculus. But how does it relate to the area problem? Let's define distance traveled first. I'll use delta S, which is equal to delta S divided by delta T times delta T. Notice that the delta T's could divide out, but I don't want them to because delta S divided by delta T is a rate. And we could work with that because this is really the same as distance equals rate times time, such that the rate is constant. But shouldn't there be a way that we could do this when the rate isn't constant? Whoa. Chill out. Let's try to visualize this first. We could take time and plot it on the x-axis and the rate and plot it on the y-axis. That means the distance traveled is simply the area of the rectangle. Hey, that's great. We found a connection between distance traveled and area, but so far there's no problem. Let's move on. Check out this example. A car travels at a rate of 48 miles per hour for 2 hours and 30 minutes. How far does the car travel? While I don't see a problem here, I do notice that 48 miles per hour is a constant rate. So how did we even get that? Are we saying that this person driving the car traveled at a constant rate for 2 hours and 30 minutes, exactly 48 miles per hour for that entire time? I doubt it. I bet that 48 miles per hour was average. Okay, so there's kind of a problem worked in there. Well, let's just solve this problem, which is the opposite as the problem we talked about in lesson 1A. We just take 48 miles per hour, multiply it by 2.5 hours. The hours units cancel out, and we end up getting 48 times 2.5, which is 120. We could take those numbers and plot them on the graph that we already created, and so it gets a little bit more real. So we have 2.5 on the x-axis, and then 48 on the y-axis. And then that area of the rectangle is 120, which is the distance traveled in miles. But again, what if that rate changes all the time? Like it's 40 and then 50 and then 52 and 49 and 13 and 0 and all of that, anything in between. There must be a way to solve that, right? To solve that area problem. If we explore the idea of infinity, we just might be able to get closer to solving the area problem. Consider a gallon of water is divided equally into teacups. Find the amount in each teacup and the total amount in all teacups for these 4 situations. So for number 1, we have 10 teacups. That means that we take a gallon and divide it by those 10 teacups. and we have 1/10 of a gallon in each teacup. Okay, not bad. And we still have a whole gallon among all the teacups. Number 2, to the right, 100 teacups. Well, that means we take a gallon and we divide it by 100, and that's how much is in each teacup. 1/100th of a gallon. And still, there's 1 gallon among all of the teacups. We're getting somewhere, I think. Number 3, 1 billion teacups. That is a whole lot of teacups. That means that in each teacup, there is 1/1 billionth of a gallon. And all the billion teacups have a total of 1 gallon. Okay, number 4, an infinite number of teacups. Well, this is impossible, but let's play anyways. Each teacup would have 1/infinitieth, 1 over infinity, gallons in each teacup. That doesn't make much sense, but still we'd have a gallon among all the infinite number of teacups. Well, 1 over infinity is pretty much 0, but it's not completely 0. So all of these infinite number of teacups really would have just a tiny, 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 tiny bit of water in each teacup. So are we saying that it's possible to solve the area problem by taking, instead of a minute or 30 minutes or hour, make it even smaller into 1/infinitieth of a minute and finding the area of that rectangle? Wow, that sounds like a lot of work. I think it's about time I tell you how the definite integral helps us solve the area problem. Warning, this will get quite technical, but stick with me because the example that follows is very, very practical. Let's start with a rate function, I'll call it f of x, on an interval a comma b, a closed interval, one that includes the endpoints. Divide the interval into n subintervals, so b minus a divided by n. That value is equal to delta x, which we'll use later. Let's continue by creating 2 columns. The left column is how to estimate area with rectangles. The right column is how to calculate with infinite rectangles. 2 different but connected things. To estimate area with rectangles, there are 3 steps. Step 1, choose x sub I as a left or right endpoint. It could also be a midpoint. X sub I, meaning if there are 6 intervals, then we're choosing 6 i's. And don't worry too much about this, it'll make more sense later. Step 2, calculate f of x for each endpoint. So those x's that we just chose, we're going to plug those into the function and find out the y values for each endpoint. Then step 3, we'll calculate area of each rectangle. So meaning all of those x values that we chose, there are rectangles in between them. And we'll find the area of each individual rectangle, as long as there aren't too many. The area of all of the rectangles together we can write as a Riemann sum. It's the Riemann sum from I equals 1 to n. So remember, n is how many intervals, the subintervals, of f of x sub I, that's x sub I plugged into f, times delta x. So the delta x we defined earlier, that's just the width of each subinterval, which is really the width of the rectangles. And then if we plug in those x values that we chose, those are basically the bottom left and the bottom right endpoints of the rectangle, or the vertices. So we plug those values in to get the height of all of the rectangles. So we're adding up all of the areas of each individual rectangle. While estimating the area underneath the curve is great and all, we want to find the actual value, the actual distance traveled. So here's how to do that in 3 steps. Step 1, choose any x sub I in the subinterval, meaning it doesn't have to be a left endpoint, a right endpoint, or a midpoint, just any x sub I in each individual subinterval. Step 2, take the limit as delta x approaches 0 or n approaches infinity. We'll learn more about limits later, but of course we need to make the size of these rectangles super skinny so that we could accurately find the area under the curve. So delta x approaching 0 means that the width of each rectangle used to be however wide, and now we're making it super skinny, almost nothing. Or n approaches infinity, meaning in the same interval, we'll use an infinite number of rectangles instead of a finite, kind of like number 4 with the teacups. Step 3, calculate the area accurately. That's a pretty vague statement, but what it really means is that when we use an infinite number of rectangles to approximate the area under a curve, it becomes very, very accurate. But it also means that there are some sub-steps that require more knowledge about the derivative to even get into right now. But I'll share the formula anyways. Here it is. The area under the curve, or distance traveled, is equal to the integral from a to b, the integral symbol is just a tall skinny s, of f of x dx. dx is the infinitely small width of the rectangle. It's called the differential. And f of x is the height of each infinitely small rectangle. A is considered just the lower limit and b is the upper limit, but those are just the values that show up in the setup of all of this, that interval that we started with originally. Like I said, evaluating this integral requires more knowledge about the derivative as well as calculus in general, but we can evaluate the Riemann sum in the left column. So let's do that. When I estimate area with rectangles, I like to create a table like this to help me organize my work. Here's the example. Use the 5 rectangles in the figure to estimate the area of the region below the curve f of x equals x squared plus 1 from 0 to 5. Let's check out the graph. I want you to see that the function is on the graph and we only see the right side of the parabola. Think about that curve as the rate function, and we're trying to find the area underneath the curve. But notice that the rectangles don't fill up all of the area underneath the curve. So this is an estimation. So we started with f of x on an interval. Now we divide that into n subintervals. So that interval, 0 to 5, 5 minus 0 is 5, divided by the number of rectangles, which is 5, equals 1. That means all of the subintervals are 1 unit wide, so we could fill in the subinterval column. 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 5. Also, delta x is equal to 1, which is the base of every single rectangle, so we could fill that in. We're on step 1 now, so we're choosing a left or right endpoint, but notice that it was already chosen for us. Look at the graph. There's a point at 0, 1. Then a rectangle sketched to the right of that. Then go to x equals 1 and up to the curve, y equals 2. Another rectangle was sketched to the right. So we're starting at the left endpoint and sketching the rectangle based on that. So 2, 5, and 3, 10, and so on. So we're choosing the left endpoint. So let's look in the subinterval column. The left endpoints are 0, 1, 2, 3, and 4. So in step 2, we'll calculate f of x for each of those endpoints. So f of 0, f of 1, f of 2, f of 3, and f of 4. F of 0 is 0 squared plus 1, which is 1. F of 1 is 1 squared plus 1, which is 2, and so on. So we have 1, 2, 5, 10, and 17 for our heights. Now we're ready to calculate the area for each rectangle, but notice the base is just 1, so our area is the same as height. It's not always like that. The base could be any positive number, really. So the first area is 1 times 1, which is 1, 1 times 2, which is 2, 5, 10, and 17. Which means our sum is 35. The sum of all of the areas of the rectangles is 35. But remember, that's just an estimate, and there was some area left over underneath the curve that we didn't account for. So this is a lower bound for the area underneath the curve, the total distance traveled, if you will. If we'd like to find the upper bound, we could choose the right endpoint, and we'd get a number larger than what the actual area is. And if we want to improve our estimation, we could use more rectangles. But there comes a point when the calculations get too tedious, then we want to consider the definite integral. I'm back. I hope you appreciated how practical that last example was. Usually when we study that topic in calculus, students really like it. We pull out the colored pencils and shade the rectangles based on whether it's a left endpoint or right endpoint. And like I mentioned, midpoint is also a thing too. Let's circle back to computing distance traveled. Here's the example, our last one. A car travels at an average rate of 56 miles per hour for 3 hours and 30 minutes. How far does the car travel? I want to point out two things. Number one, this example explicitly says average rate. And number two, this is very much like the first example that we did together, so it's not really new. We could solve this graphically by plotting the line y equals 56 up until time equals 3.5, and we find the area of the rectangle, and that's the answer. But based on the work that we've done already, I can sketch that line as a curve showing that the car travels greater than 56 miles per hour or less than 56 miles per hour back and forth until 3.5 hours has been reached. So what's neat about that is once we know more about calculus and the derivative and the integral, we can use the integral to actually find the area underneath the curve, but then we could relate that to the area of the rectangle, basically by working with the average value of a function, which is a thing too. To solve this numerically, we'll just take 56, multiply it by 3.5, and we get 196 miles. So how far does the car travel? 196 miles. We've reached the end of this video lesson, and I want to thank you for sticking with me. Just so you know, definite integrals account for almost a half of the Calc AB course. When I teach it, we usually study it from January through mid-April. And in Calc BC, definite integrals is about 1/4 of the class. If you have any questions or comments, feel free to comment below or contact me directly. Hey, thanks a lot.